Welcome to this module. In the last module what we have seen micro machining techniques along with the lithography, right. We have taken an example of a micro heater, how to fabricate a micro heater. If you just go through that particular lecture, you should now know what are the process steps for, if you talk about photolithography, right. For the first step you have to coat the wafer with what? Photoresist, right. Photoresist, what kind of photoresist are there? Positive and negative, mask, bright field and dark field, right. Now after coating the photoresist on the substrate, it can be your oxidized silicon wafer, it can be glass, it can be any other material on which you want to fabricate your sensor or actuator, right. Then what is the next step? Next step is for pre-baking. Pre-baking is done at 90 degrees centigrade, correct, 1 minute hot plate. Next step is you have to load the mask. When you load the mask, you have to align it. I will talk about alignment at some point of time. Once you align it, you have to make a hard contact. Hard contact means that actually the mask is connecting the wafer, is contacting the wafer, right, hard contact. And then what is the next step? You have to expose the wafer. You expose the wafer using what? Using UV light, right. After you expose the wafer, next step would be to develop the wafer. Once you develop the wafer, the next step would be hard bake, and after that you are ready with your pattern. If it is if there is a metal, you have to etch that metal and finally remove the photoresist or strip of the photoresist using acetone, right. So, you should remember this process because this is more or less similar for a lot of fabrication, for fabricating lot of sensors, alright. Now after that we have studied micro machining, in which we talked about bulk micro machining and surface micro machining. Once you understand bulk micro machining and surface micro machining, we took an example of a cantilever fabricated using surface micro machining and a diaphragm fabricated using bulk micro machining. Then we discussed about there are different materials for etching the silicon. It is a potassium hydroxide or it can be TMAH, both has their own pros and cons. For example, if you take KOH, which is potassium hydroxide, the temperature is at 80 degrees centigrade, while TMAH we have temperature around 25 degrees centigrade. With KOH you have faster etching, with TMAH you have slower etching, with KOH you have a rough surface, with TMAH you have a smooth surface, right. So, these things you have to take care when you are actually fabricating your device, right. Now a very important tool that is used for bonding silicon to silicon or silicon to glass or glass to PDMS, right. So, there are several tools and that more or less we can say it is a wafer bonding or PDMS and glass bonding or glass to silicon bonding. So, several names are there, right. We call it like anodic bonding, we say for when it is glass to silicon bonding. Also we say direct bonding, intermediate layer bonding. So, let us see in this module what exactly wafer bonding is and what is the high aspect ratio fabrication using DRI, and we will take an example of a microfluidic platform that will be fabricating using the bonding technique, okay. And in that we will use soft lithography. So, what exactly soft lithography means, right. So, if you see the screen, the wafer bonding, the method that involves joining 2 or more wafers together to create a wafer stack. So, if I take a silicon wafer, right, and if I have another wafer which is like this, so I keep on joining the wafers one over another, it becomes a stack of silicon wafer, right. So, this is a method which is called wafer bonding. 3 types of wafer bonding, one is direct bonding, second one is called anodic bonding, while third one is called intermediate layer bonding, okay. And all require substrate that are flat, smooth and clean. You see the bonding process, if the surface roughness is there or if there are particles are there, then that particular area will not bond clearly, right, it will not bond. So, for a good bonding, for a strong bonding, we need that the substrate should be clean, the substrate should be flat and substrate should be smooth. So, it should not be rough, right. So, that is what is very important in the bonding. Now like I said, we will take an example of microfluidic sensor or device. Before that, let us understand what is the deep reactive ion etching, alright. So, you know if I want to create a pit, right, if I want to etch silicon wafer, what I will do? If wet etching, I just told you, right, I will save silicon dioxide in this area and then here I will etch it, right. So, if I want to etch about 5 microns is fine, I can just quickly etch it using either RI or wet etching, right. Wet etching can also be used for bulk micro machining, but let us understand that we want to etch only 5 microns. For 5 microns I can use reactive ion etching, alright, which is a dry etching. We can also use wet etching, but if I want to etch 400 microns out of 500 micron silicon wafer, that is the thickness of silicon wafer is 500 micron, assuming the silicon wafer is of 4-inch diameter, right. Then if I want to etch 400 microns, I will use a process called deep reactive ion etching, right. So, what is deep reactive ion etching? You can see here on the slide, the deep reactive etching has fluorine and SF6, it also has CFX, it also has SFX like what I told. And what exactly this does, what is the process? So, the first is that it enables very high aspect ratio etches to be performed in silicon substrate. You can see here the cross section of silicon wafer, right, where trenches are formed using the DRI. You can see these trenches that are formed, see here all the way down, these trenches, these are formed using DRI, alright. So, these trenches are, it is a deep trench that we can fabricate or form in the silicon wafer. Now, how does this work? So, first is if you have silicon and you have a mask, what is this mask? It is not your bright field or dark field mask. Okay. In silicon, if I use silicon dioxide, then silicon dioxide will act as a mask. What does that mean? That the SF6 or any material that I am using for etching my silicon wafer, this material, this gas will not etch silicon dioxide. So, when you say it will not etch silicon dioxide, what does it mean? It means that it will etch, but the etching rate is extremely small compared to your silicon wafer. The etching rate of silicon dioxide is extremely small compared to etching of your silicon. That is why silicon dioxide can be used as a mask, alright. So, that is what I mean. Now, if I use this gas, then what will happen? It will start etching, like you can see, right, it is etching silicon, right, and then I will use another gas which will form a polymer layer, right, CF2, if it will form a polymer layer. So, it will just smoothen this wall like this, right. Now, again I will use the same gas, right. So, what will happen? Again it will start etching from the bottom, but the side will be comparatively smoother. In wet etching, what happens? I am etching like this, it goes like this and it comes like this. These sides, this one, walls, right, these walls are not smooth, these walls are rough. If you use DRI, then you will have a much more smoother wall compared to your wet etching, Wet etching is KOH or TMAH, right. So, the wall smoothness or the smooth wall we can obtain using deep reactive ion etching. Also, if you see that the side walls of the etched holes are nearly vertical, depth of the etch can be of hundreds or even thousands of microns into the silicon substrate. So, when somebody says 1000 micron, that means that depending on the thickness or depending on the diameter of the wafer, right. We are talking about 4-inch wafer. If you use larger diameter, then the thickness also increases. For 4-inch wafer, the silicon thickness is close to 500 micrometers, right. So, DRI can be used for etching few hundreds to few thousand microns of silicon wafer, which with much more smoother wall compared to your wet etching. So, this is what you have to understand. Now, let us take an example of soft lithography or a microfluidic platform. So, let us understand a very simple platform. This is how it should look like. There is a channel and then we are bonding it, right. So, that means you have this, here there is a flow, we can flow gas, we can flow liquid into this channel. this is your PDMS, or let us say this is your glass, this is your glass, and this is PDMS. Now, how we will create this kind of microfluidic platform? This is a microfluidic, right? This width, this one will be of, let us say 100 micrometers. The depth is again say 50 micrometers, right? Width is 100 micron, depth is 50 micron. It is a microfluidic channel, all right, and we will flow either a liquid or a gas through this microfluidic channel. Right, so that is our device. Now, how can we fabricate this device? So, let us see, we will start one by one. First step is we need to create this PDMS, right? PDMS should look like this. Please find it out what does PDMS means, right? This is your homework, alright. So, you take a silicon wafer, then you grow silicon dioxide. You can grow silicon dioxide using thermal oxidation. Next step is that spin coat photoresist, spin coat photoresist. So, I have spin coated my photoresist. I am using positive photoresist. This is my SiO2, silicon, this is positive photoresist, right. Next step is soft bake, right, soft bake 90 degree centigrade for 1 minute on hot plate, cool. Now, next step is, alright. So, this is silicon dioxide, you know it, right, and there is silicon and silicon dioxide. So, next step would be, or let me just draw it here, so it becomes easier. I will draw it here. Okay. So, what we have? We have silicon dioxide, then we have photoresist which is already soft bake. On that I will load a mask, this is my positive photoresist, this is silicon dioxide, this is silicon, this one is silicon dioxide, right, and my mask would be like this. Right, be with me. Mask, this is my bright field mask, After this we will expose the wafer with what? UV, right, expose the wafer with UV. Next step would be I will develop this wafer, develop wafer means you are developing photoresist, okay. You will develop the photoresist. When you develop photoresist, what you will have? You will have silicon dioxide, and photoresist. correct, because we have used positive photoresist, that means that the unexposed area will be stronger, right. This is unexposed area and that is what it is stronger. Next step would be I will dip this wafer in buffer hydrofluoric acid, BHF. What is the advantage of dipping the wafer in BHF? BHF is etchant for silicon dioxide, right, but are we missing any step in this? After developing photoresist and you have this pattern, are we missing anything? Yes, right, we have to perform hard bake, and that is done at 120 degree centigrade for 1 minute on hot plate. After hard bake, I will dip this wafer in BHF, which is SiO2 etchant, ETCHANT, etchant. All right. So, when I do that, what will I have? I will have silicon, positive photoresist and SiO2. All right. Then the next step would be that I will dip this wafer. So, I will just remove this, right, I will remove this, let me draw it here, so it becomes easy. This is my glass, this is PDMS, all right. So, I will just delete it so that you do not get confused. All right. After this, next step would be that I will remove my photoresist. How can I remove my photoresist? If I dip this wafer in acetone, my photoresist will be stripped off. If my photoresist strips off, what will I have? I will have silicon with silicon dioxide, correct, silicon with silicon dioxide. Now, I will perform deep reactive ion etching, right. I have videos for you that it will help you to understand how DRI works. Right now, you have just seen in the previous slide how the process flow in DRI works. There is a etching gases and then there is a polymer which will smoothen the wall, again there will be etching, again there will be polymer, so that your wall surface is smooth. Now, after DRI, what will happen? I will have what will I have? My silicon will get etched in these regions, right. See, in this region silicon will get etched and silicon dioxide will be intact, and the silicon below silicon dioxide, this everything is silicon, the silicon below silicon dioxide is also intact, right. So, if I want to draw it, it will look like this, right. So, silicon dioxide will act as a masking layer, silicon dioxide acts as a masking layer, all right. Now, what is the next step? After this, silicon is there, silicon dioxide is there, right. I will again dip this wafer in buffer hydrofluoric acid, BHF. If I dip this wafer in BHF, what will happen? What will happen? I will have, let me just draw it on the next page. Okay. You remember this? You remember this. Okay. So, if I dip this wafer in buffer hydrofluoric acid, what will happen? I will have silicon in this form, right. This is a straight line. Alright, this silicon, this is what we get if I dip this wafer into the buffer hydrofluoric acid. Okay. Next step is I will pour PDMS. What I will do? I will pour PDMS onto this silicon. So, what will happen? My silicon wafer is there, right, and on this what I have? I have my PDMS, correct. I have PDMS. After pouring PDMS, let's let's just leave it. Okay, let's just leave it like this. So, okay. So, PDMS, after that what is the next step? You have to cure it, curing. Okay. Curing would be done depending on the thickness of PDMS. There is a data sheet, that is we can use the data sheet to understand what will be the curing temperature. Is it 125 degree centigrade, is it 90 degree centigrade, right, and for how much time you have to cure it, right. So, once you perform curing, right, then you can strip off the PDMS. That means you will have PDMS which looks like this, correct, because if I strip off from this, then I will have this shape of PDMS, which is opposite to this one, is not it. Here I have hill here, I have a valley here, right, because I am pouring PDMS on the silicon. So, this silicon substrate is called mold, Now, I have PDMS. What to do with that? I will take a glass wafer, I will load PDMS in this direction. So, this both thing we will keep inside an oxygen plasma system, we will keep inside an oxygen plasma chamber, alright. Both things will put or load inside an oxygen plasma system. Now, what will happen when we do that? You have to make sure that the surface which you want to bond, that means this surface you want to bond, right, you want to, this surface you have to bond with the glass. So, surface that you need to bond is on the top side, you see top side here, correct. I have flipped this wafer. So, the top side is in contact with the oxygen plasma system, and same thing goes for glass. After that is done, the glass is there and you have to take that PDMS, take PDMS and bond it, press it, apply a uniform pressure. This is your PDMS, this is your glass, right. If you flip it, it becomes like this, there is a glass, there is a PDMS, and you have this microfluidic channel, right. So, if you see, this is the one that we got, alright. So, now if I want to make more of this microfluidic devices, what I want? I just want to use my silicon mold, I have to just use silicon mold, right, and I will keep pouring PDMS, cure it, strip it off, I will get this particular design. Again I cure another PDMS, cure it, right, pour PDMS, cure it, I will have second design. Again I will do the same process, I can do it as long as my mold is intact, my mold is not broken. That means we are performing a lithography, but not using a conventional technique of using lithography technique like UV exposure, photoresist coating, but instead of that we are using a mold and we are pouring PDMS and stripping it off. This is called soft lithography. What is called soft lithography, alright. So, if I have a PDMS and if I have a mold, if I pour PDMS on that mold, I cure it, I strip it off and I can do it 100 times, I can make 100 devices like this. I just require an oxygen plasma system, is not it. So, let us quickly see once again this process and we will end up the module at that particular point, alright. So, if you see the screen, we started with silicon, right, we started with silicon wafer, then we oxidize silicon wafer using thermal oxidation, then we have spin coated positive photoresist followed by soft bake at 90 degree 1 minute. Next step was to load the bright field mask, right, and expose it with UV, after which we will have to develop the photoresist. After developing photoresist, you will find that the area which was not exposed got stronger, and then you had to perform a hard bake at 120 degree centigrade for 1 minute, right, followed by a BHF dip. BHF will etch silicon dioxide. So, you will have this wafer. Now, you do not require your positive photoresist. So, you have to dip this wafer in acetone, correct. So, when you dip this wafer in acetone, you will have silicon dioxide and silicon. If I use DRI, then DRI will etch silicon except the area which is protected by silicon dioxide, and then you will have this structure which is with silicon dioxide and silicon. If I dip this particular wafer in buffer hydrofluoric acid, I will have my mold which is silicon mold, on which if I pour PDMS, I cure it, I will have my PDMS with my microfluidic or the patterned PDMS, and then I will take a glass and PDMS, and then I will load this with upside on the top surface which is used for bonding, right. I load in a oxygen plasma system, and then we will cure it, we will connect the glass or attach the glass with PDMS to make a bond, right, which is your bonding technique, and apply a uniform force, right, for 15 seconds to obtain a microfluidic device. Alright. So, oxygen plasma followed by PDMS and glass bonding to form your microfluidic device. So, this is what we have learned in this particular module, and let us see in the next module what we will take as a different example, right. I hope you understand how important the bonding is, because when we talk about the micro machining, we talk about microfluidic channels and we talk about the screening platforms, we have to use microfluidic devices, and when we talk about microfluidic devices, you have to go through this particular process which is your soft lithography. Alright. So, we will end this particular lecture at now, and in the next lecture we will see where are the MEMS used, what are the MEMS operation, what are inertial sensors, and many more things. Alright. Till then, you take care, have a nice day, bye.